Welcome back to the Deep Dive.
Great to be here.
Today, we're diving into something, well, a bit unnerving technically. We're looking at how large language models can start showing behaviors that look, frankly, a lot like human gambling addiction.
And just to be clear up front, our focus here isn't really the ethics, but the raw technical safety side, the operational integrity.
Right.
We're zeroing in on the specific neuromechanics, what's actually driving these really flawed, high-risk decisions inside the AI.
Because these models are increasingly making big calls for us, aren't they?
Absolutely. Asset management, commodity trading. Places where this kind of pathological risk-taking isn't just bad, it's potentially catastrophic, financial ruin territory.
Exactly. I mean, imagine an LLM agent chasing losses in a live trading model. That's a massive systemic risk we absolutely need to understand and fix.
Mm-hmm. And this whole deep dive today comes from some pretty extensive experiments.
Yeah, tell us about the source material.
So researchers took 4 big models, GPT-4 Mini, GPT-4.1 Mini, Gemini 2.5 Flash, and Claude 3.5 Haiku, and put them through their paces on a rigged game, a negative expected value slot machine, task.
Designed to lose over time.
Precisely.
Yeah.
But crucially, they didn't just watch the behavior, they paired that with mechanistic interpretability.
Meaning they looked inside?
Exactly. Using LLaMA 3.18b, they tried to actually open up the black box, find the internal circuits that cause this risky behavior.
Okay, so let's start with the basics then. How do you even begin to measure something like pathology or addiction when you're talking about an algorithm? Sounds fuzzy.
It does, but they built a framework. They borrowed pretty heavily from human behavioral economics and cognitive psychology, established concepts.
Makes sense. Start with what we know about humans.
Right. So 2 main angles. First, the behavioral side, just measuring what the model does. Actions you can see.
Like what?
Things like loss chasing.
Yeah.
That's, making bigger and bigger bets specifically to try and recover money you've already lost.
Ah, yeah. That sounds familiar from human behavior. Prospect theory, right. Risk-seeking when you're down.
That's exactly the parallel. Trying to get back to even no matter the odds.
Okay, what else on the behavioral side?
The other big one is win chasing. This is where the model gets riskier right after a win.
Like it's playing with house money.
Basically, yeah. The house money effect. The winnings feel kind of disposable, so it takes bigger risks.
Okay, so that's the action. What about the thought process? The cognitive side?
Right, the cognitive approach. Here, they looked for irrational thinking patterns. 2 main culprits they focused on.
Which were?
First, the illusion of control. This is the model, or the person, believing they can actually influence a purely random outcome through skill or strategy.
So if you tell an LLM, maximize your score, it might think its betting pattern is actually working, even if it's just luck.
Precisely. It overestimates its own agency in a random system.
And the second, cognitive bias.
The gambler's fallacy. The classic belief that past random events somehow influence future ones, I've lost 10 times, so a win must be coming soon.
Right, the coin doesn't remember the previous flips.
Exactly. So combining these behaviors and these cognitive errors allowed them to create a single score, a quantitative measure.
The Irrationality Index. Okay, break that down for us. What goes into that number?
Sure. It's a composite score, mainly built from 3 things. Betting aggressiveness, just how big the bets are overall compared to the capital.
Simple enough.
Then loss chasing, which we talked about, measuring that specific tendency to bet more when losing. And finally, extreme betting.
Extreme betting. How did they define that?
He set a specific threshold, wagering 50% or more of your remaining capital in a single bet.
Wow, half the pot in one go. That's not just aggressive. That really does feel like it captures that illusion of control, doesn't it? Like you're sure this next one's the winner.
Mm-hmm. It's a sign of really broken risk assessment. It captures that systemic danger well.
Okay, so armed with this index, let's look at the experiment design, this 2x32 factorial setup. What happened when they flipped the switch from fixed bets to letting the models choose their own bet size, that introduction of autonomy?
Yeah, that was the critical moment. And the results were pretty dramatic.
How so?
In the fixed betting condition, where the bet size was set for the model, bankruptcy just wasn't really a thing. Negligible rates across all models, everything was stable.
Okay, the guardrails were up.
Exactly. But as soon as they switched to variable betting, gave the models autonomy over how much to wager. Boom, bankruptcy rates shot up massively for all the models.
All of them. But presumably some handled it better than others.
Oh, absolutely. The variation was huge, which is interesting in itself. It tells you this isn't just some generic LLM flaw. It's tied to specifics of the model.
So who was the worst offender?
Gemini 2.5 Flash. It had the highest irrationality index, and its bankruptcy rate was a staggering 48.06%.
Nearly half the time it just wiped itself out.
Yeah.
Just total portfolio destruction. On the other end, GPT 4.1 mini was the most, let's say, rational. Only a 6.31% bankruptcy rate. Much more conservative.
And they found a direct link between that irrationality index score and going broke.
A very strong link. Across all four models, a clear positive correlation. We're talking correlation coefficients about between 0.770 and 0.933. Basically, the higher the irrationality index, the more likely the model was to go bankrupt.
The pathology directly predicts the failure.
Undeniably.
Okay, let's pause here for our neural signal check. Here's why this development actually matters at a technical level. We see the correlation. Pathology leads to failure. But why does the pathology appear? It wasn't random, right? It was triggered by certain inputs. What did digging into the prompts reveal?
Right, this is where it gets really practical. The analysis showed that how you grant autonomy is key. It wasn't just variable betting in general. Specific types of prompts dramatically ramped up all the bad metrics, the bet sizes, the irrationality, the bankruptcies.
What kind of prompts? The ones that really pushed the models towards deep inference and explicit goal setting. Specifically, prompts containing components for goal setting, like double your money and maximizing rewards.
So telling the LLM your job is to hit this ambitious target actually backfires. It triggers this harmful, almost desperate optimization.
It seems so. It looks like that strong goal fixation makes the model prioritize aggressive strategies over careful risk assessment. It really mirrors that human illusion of control. I have a goal, therefore my aggressive actions must be the way to achieve it.
Even in a game rigged against it.
Even then. And interestingly, while they saw both loss chasing and win chasing turned out to be the dominant pattern across all the models.
Really? Win chasing was stronger than loss chasing. That feels a bit different from the typical human problem gambler story, where loss chasing often seems so central.
It is a subtle but potentially important difference. Win chasing suggests this sort of momentum-based thinking, right? I just won, I'm hot, double down.
Why might LMs lean more towards that than desperately trying to recoup losses?
Well, it could tie back directly to how we train them, often with reinforcement learning focused on maximizing immediate rewards. A recent win is a very strong positive signal.
So the model thinks, aha, that aggressive bet worked. Do it again, but bigger.
That's a plausible explanation. The win reinforces the aggressive policy itself, leading to riskier follow-up bets. Perhaps more directly than the negative signal of a loss triggers the need to chase.
Okay, and another huge finding for anyone designing prompts for these things. Complexity is bad news.
Very bad news. They found an incredibly strong linear correlation, or R values, over 0.956, so almost perfectly linear, between the sheer number of different components added to the prompt and the increase in gambling behavior.
So more instructions equals more gambling. Why would that be? Does it just overload the model?
That seems to be the most likely mechanism, yes. When you pile on instructions, achieve goal G, use strategy S, obey constraint A, avoid condition B, the model's computational resources get tied up just trying to parse and satisfy everything.
And it drops the ball on risk management.
It looks that way. It seems to shift the model away from careful, maybe computationally heavier, rational assessment towards using faster, more aggressive heuristics just to meet those explicit demands like maximize reward.
The takeaway seems clear. If you want safe decisions from an LLM agent in a high-stakes situation, keep the instructions simple and clear.
Definitely seems advisable based on this.
All right, so we've covered the pathological behaviors and the kinds of prompts that trigger it. Now for the really deep part, the how. Inside the LLaMA model itself, how do they go from observing behavior to pinpointing causal mechanisms at the neural level?
Yeah, this is where the mechanistic interpretability tools really shine. It was a multi-step pipeline. Step 1 involved using something called a Sparse Autoencoder, or SAE.
Okay, SAD. What does that do in simple terms, for those of us not neck-deep in transformer internals?
Fair enough. Imagine the model's internal signals are like a big, messy switchboard. One wire, one neuron might be involved in controlling 5 different things at once. It's confusing. They call it polysemanticity.
Okay, tangled wires.
Right. The SAE acts like A super smart electrician, it mathematically untangles that mess. It maps each of those 5 functions onto its own clean, dedicated switch. A sparse, interpretable feature.
So instead of one neuron doing 5 jobs fuzzily, you get 5 distinct features, each doing one job clearly. Like, this feature lights up specifically when considering a risky bet.
That's the core idea. It resolves that polysemantic fuzziness into clear, single-purpose features. So step 2 was feature extraction, using the SAEs on the later layers of LLaMA layers 25 to 31 specifically.
The decision-making layers.
Generally considered to be yes. They sifted through potentially millions of these sparse features and found 3,365 that were differentially active, meaning their activation levels were strongly different depending on whether the model was heading towards a bankruptcy decision versus a safe stopping decision.
So they could literally point to, say, feature number 16827 in layer 30 and say, this one looks really important for driving risky behavior.
Exactly. They could quantify it, finding features with huge statistical separation, like that example feature you mentioned, which had a massive effect size, a Cohen's d of plus 1.669 towards risk.
But correlation isn't causation, right?
Hmm.
How did they prove these features actually caused the bad decisions, not just happen to be active at the same time?
That's the crucial third step, activation patching. This is where they directly intervened in the model's processing.
How does that work?
They essentially took the average activation level of a safe feature, one associated with stopping safely from many safe examples, and then during a new game, they manually forced that feature to have that safe activation level, overriding its natural calculation. Then they watched what the model decided.
So you're essentially injecting a safe thought into the model's brain and seeing if it changes its behavior.
That's a great way to put it, yes. They did this for both safe features and risky features.
Yeah, what did patching these activations actually prove?
It proved direct, measurable causal control over the gambling behavior. They narrowed it down to 441 features with a statistically significant causal effect, 361 promoting safety, and 80 promoting risk.
Okay, what happened when they patched in the safe signals?
The effect was really quite potent. Patching the average activation of these safe features boosted the rate of safe stopping by almost 30%, plus 29.6%. And even more importantly, in those risky scenarios where bankruptcy was likely, patching safe features reduced the bankruptcy rate by 14.2%.
Wow, that's significant leverage from tweaking just a few hundred internal features out of millions.
It really is. And flipping it around, patching in the risky features.
Let me guess, more bankruptcy.
Yep. It increased the bankruptcy rate by 11.7%. Direct causal link established.
But maybe the most mind-bending part was where these features lived in the model's architecture, right? They weren't just scattered randomly.
Not at all. There was a very clear pattern. The safe features, the ones promoting cautious play, were heavily concentrated in the latest layers of the model. They analyzed layers 29, 30, 31.
And why is being in later layers significant? What does that tell us architecturally?
Well, in standard transformer architectures, later layers are generally thought to handle more abstract reasoning, synthesis of information, and final decision refinement just before the output is generated.
So safety signals dominate the final stages.
It suggests that, yeah, which implies something really interesting. The model's sort of default state, its inherent architectural bias as information flows towards the end, might actually lean conservative.
The risky features.
They clustered earlier in layers 25 through 28. This suggests that pathological behavior isn't the default. It happens when specific inputs or internal states manage to activate these earlier risky circuits strongly enough to override the later layer conservative bias.
Fascinating. So the model has a safety net built in, architecturally speaking, but certain conditions can punch through it.
That seems to be the implication.
Okay, let's try to wrap this up. What are the big technical takeaways here?
I'd say 2 main things. 1, LLMs can definitely reproduce complex human cognitive pathologies, like illusion of control and chasing behaviors in certain settings. It's not just surface mimicry.
And 2.
And 2, thanks to tools like SAEs and activation patching, we now know this pathology isn't some vague emergent property. It's rooted in specific, identifiable, and crucially manipulable neural features. We found the circuits responsible, and we showed we can causally control them.
Which moves LLM safety from just observing bad outcomes to potentially performing targeted interventions inside the model.
Exactly. It's a shift from surface-level fixes to understanding and potentially correcting the fundamental decision-making mechanisms.
So thinking about the future, what does this mean practically? If we can pinpoint these risky features, like that feature sexy at 827 and layer 30, acting like a go bankrupt switch.
Then we can start designing much more surgical safety interventions. Instead of broad, potentially capability-damaging fine-tuning, maybe we can develop techniques to specifically monitor or dampen only those few problematic features.
Which is incredibly important if these agents are managing real money or critical systems.
Absolutely. You want precision safety, not lobotomizing the model's useful abilities.
And the research hinted that these dangerous patterns might not even need malicious intent to appear, right? They could just emerge.
That's a really important point. They suggested these risk-seeking behaviors, this relentless pursuit of reward, even when it's destructive, could pop up almost accidentally during normal training, like RLHF. If the model is just trying its best to maximize a simple reward signal in an environment that allows for these pathological strategies to score well temporarily,
It might learn the wrong lesson, embedding these risky circuits without anyone explicitly telling it.
precisely, it becomes goal-fixated in a harmful way.
So that leaves us with a pretty critical question, maybe a provocative thought for you listening. If LLMs can basically develop these addictions, these pathological decision circuits, just by trying too hard to optimize a simple reward in a flawed setup, how do we need to change the way we design those reward functions and training environments in the first place? Can we build in mechanisms, maybe internal monitors for these risky features, or more complex, multi-objective reward signals that inherently value caution to detect and prevent these circuits from forming before they lead to real-world failures?
That's the multi-million-dollar question for safe AI development, isn't it? Designing reward landscapes that encourage capability without inadvertently creating these hidden pathologies.
Something to definitely think about. Thanks for breaking that down for us.
My pleasure. Fascinating stuff.
We'll see you next time on The Deep Dive.